Have you ever noticed how mayonnaise is still and stubborn while in the jar, but once you shake or stir it, it becomes really easy to spread? This everyday experience is actually a great example of a fundamental concept in mechanical fluids called viscosity. Viscosity is a fluid's resistance to motion or to flow. A low viscosity fluid, like water, would mean that it's easy to flow. On the contrary, a high viscosity fluid could be found in honey because it's very thick, so it's very hard for it to flow. Specifically, mayonnaise can be considered to have a very high viscosity, which can be translated when you think about it being still and stubborn in the jar. However, what makes it interesting is that its viscosity will change depending on how much force you apply to it. This dependence between force applied and viscosity means that mayonnaise is a non-Newtonian fluid. Most fluids like water and oil are actually Newtonian fluids, which means that their viscosity will remain constant no matter how much force and at what rate it is applied. Mayonnaise behaves very differently, however. When it is at rest, it'll have very high viscosity, and it'll be very stiff and very hard for it to move. On the contrary, when you shake, stir, or spread it, the viscosity will become lower and it'll be easier for the fluid to move. In order to study this behavior quantitatively, we use a tool called a rheometer, like this end-to-end rheometer here in the lab. Instead of just saying a fluid is thick or thin, a rheometer allows us to measure exactly how a fluid responds to applied forces. In this instrument, a small sample of mayonnaise is placed between two surfaces. The rheometer then applies a controlled rotational motion, creating what we call a shear rate, and measures the increasing shear stress, which are the forces the fluid resists with. From this, we can calculate viscosity and see how much it changes as we increase the applied force. If we were to plot viscosity versus shear rates for mayonnaise, we see a clear trend. As shear rate increases, the viscosity will decrease. That curve is a signature for a shear thinning fluid. And it explains why mayonnaise is still when it is at rest, but it suddenly becomes easy to spread once you apply movement to it. Understanding this behavior isn't just academic. Rheology plays a very important part in deciding how products will behave. Take sunscreen, for example. When you're applying it to your body, you want it to spread smoothly. But once you've already applied it where you want it to stay there instead of dripping down. This balance is achieved by engineering the viscosity to be shear thinning, to be thick at rest but thin at motion. These three products behave under what is called non-Newtonian behavior. And engineers and scientists rely on tools like the rheometer we saw in order to precisely tune how they want a certain fluid to behave under applied forces. So the next time that you're eating mayonnaise, remember you're not just making lunch, you're actually interacting with a carefully engineered non-Newtonian fluid, and the same physics that we saw here in the lab applied to your sandwich.